Okay, what I've got here on the board is 3 different ways that we've seen this semester to describe a two-dimensional surface living in 3 space. And if we have 3 ways to describe the surface, we're going to have 3 different ways to describe the tangent plane. Now, some of them are related, but they're slightly different formulas for each circumstance. So the 3 ways we have to describe a surface are, it could be the graph of a function, where z is a function of x and y. One thing I find interesting about that, there we would be graphing input together with output. So x and y would be the input, z is the output. We put that together, that gives us a point in 3 space, and we're getting our surface then that lives in 3 space. Okay. We could also have a level surface. So if I have a function of 3 variables, g of x, y, z, and I set that equal to a constant, if I were graphing this function, it would give me a w value. That would be in 4 space. If I set it equal to a constant, I'm looking at a subset of the domain, or a subset of just the inputs to the function, all of those inputs that map to a specific value of k. And so I could find the level surface at a point there. Notice when it's a level surface, I need to specify the point in 3 space. If it's the graph of a function, I can just specify the input point in 2 space. I would plug that into the function, and that would give me the z value at that point. Okay. So if I'm doing the graph of a function, I'm graphing input and output. With a level surface, we're really looking at a subset of the inputs only, not the outputs, no w values involved. When I have a parametric surface, just like with a parametric curve, I'm graphing the outputs only. I'm not graphing my u and v values. They're in this plane over here that I'm mapping over to 3 space. If I were to put input and output together, I'd have a 5-dimensional graph. We don't want that. Okay. So here we're graphing the output only. Okay. And I would specify where I want to calculate the tangent plane by naming a point in 3 space. But one way of doing that would be to name the point in 2 space that my parameterization is going to send there. Okay. All right, so 3 different ways of describing a surface. How do we describe the tangent plane? Well, if I'm looking at the graph of a function, I can just use, would be the local linear approximation. So that was where we had our L of xy is equal to f at x naught, y naught. Let's just write p naught, it's faster. F at p naught plus the gradient of f at p naught dotted with x minus x naught, y minus y naught. And of course, if you're actually turning this in, work out the dot product. But basically, we're saying the z value on the tangent plane is the z value at the point of tangency plus some change. And we get the change by dotting the rate of change vector with the amount of change vector. Okay. Now, if we're working with a level surface to a function of 3 variables, here I'm just going to use point normal form. Where what's normal is going to be the gradient of g at q naught, at the point of tangency. Notice when I have a function of 3 variables, the gradient will be a vector in 3 space. When I have a function of 2 variables, this gradient is a vector in 2 space, so there's no way it could be normal to a surface in 3 space. But here this is, and I would just dot this with x minus x naught, y minus y naught, z minus z naught. And of course I'm getting 0 because if this is normal, then I'm saying this is a vector I would form by connecting 2 points that are on the plane, the specific point q naught and an arbitrary point x, y, z. So this is parallel to the plane, therefore it's got to be orthogonal to the plane's normal. Okay. Now, with a parametric surface, we are also going to use point normal form. So it's a little bit more like what we do when we have a level surface, but we're going to have a different normal vector. So I mentioned last time that if we have a smooth parametrization, the cross product of the 2 partial derivatives will be normal to the curve. That's because one partial derivative is tangent to a curve that lies on the surface. So that tangent vector will be in the tangent plane. The other partial derivative is tangent to a different curve that lies in the surface. It also is tangent to that curve, so it's going to be part of the tangent plane. And then that gives me two vectors that are both parallel to the tangent plane. If it's smooth, they're not parallel to each other, so when I cross them, I will get something that's normal. So here, I would take the partial of r with respect to u, crossed the partial of r with respect to v. That would have to be evaluated at u naught, v naught. Okay. And I would dot that. Let's actually give this point a name. Let's call it x naught, y naught, z naught. So that would be the point of tangency in 3 space. So I'd be dotting with x minus x naught, y minus y naught, z minus z naught, and of course getting 0. So it's still point normal form, but a different way of calculating what's going to be normal to my tangent plane. So let's just do an example of that. So let's say I'm working with z equals x squared plus y squared. Just my paraboloid here. Now I could, because that's z as a function of x and y, I could just calculate the local linear approximation. What I want to do instead is work it out by parametrizing it, and then just confirm that we get the same thing we would get if we did the local linear approximation. So if I were to parameterize this, I would let r of uv equal uv u squared plus v squared. Okay. So I'm just letting x be u, y be v, and then z becomes a function of u and v instead of x and y. Let's say I wanted to find the tangent plane at the point, let's find it at p naught 1, 2. So because x is u and y is v, that means in the uv plane, I'm also looking at the point 1, 2. That's just going to map then to a point here, which would be, well, let's figure it out. R of uv would just be 1, 2. 1 squared plus 2 squared would be 5. So that's going to be our point of tangency. Okay, excellent. So I can calculate the partial of r with respect to u. That's just going to be 1, 0, 2u. I can calculate the partial of r with respect to v. That's going to be 0, 1, 2v. So really nice pattern here. I'm always, if I have z was a function of x and y, I'm always going to get a situation like this, where I put u here, v here, and then just that function of u and v. So I'm getting 1 here when I take the partial with respect to u, 1, 0. And then this is just the partial derivative of this function with respect to x, except I'm now calling it u. Similarly, this is 0, 1, and this is the partial derivative with respect to y, except we switched names and calling it v. All right, excellent. So I'm going to actually evaluate these at this point, because then I just get numbers. Whoops. Let's do del r del u evaluated at 1, 2. So that's just going to be 1, 0, 2, because I'm plugging in 1 for u. Del r del v at 1, 2 is going to be 0, 1, 4, because I'm plugging in 2 for v. And so now let's take their cross product. Okay. So if I look at del r del u at 1, 2, crossed with del r del v at 1, 2, that's going to be the symbolic determinant, I, j, k, 1, 0, 2, 0, 1, 4. It does not matter, in this case, what order I cross them in, because all I care about is getting something that's normal to the surface. Now, there are going to be situations where I care whether my normal vector is pointing out away from the paraboloid or in towards the center of the paraboloid, but for the purposes of finding a tangent plane, it does not matter. Okay, so let's see what this gives us. So for the i's, I'm getting nothing minus 2. That's going to be 2. For the j's, I'm getting nothing minus 4. And for the k's, hang on a second, I said nothing minus 2. That's going to be a negative 2. I do apologize. The i's are nothing minus 2. For the k's, I'm getting 1 minus 0. I'm just getting 1. Excellent. Okay. So I can now say this was my point of tangency, so I'm going to be getting negative 2, negative 4, 1. That's my normal vector, dotted with x minus 1, y minus 2, z minus 5, and that should equal 0. Now, let's actually work that out. That's negative 2 times the quantity x minus 1, minus 4 times the quantity y minus 2, plus z minus 5 is equal to 0. Now, I had mentioned that because we were working with a surface that I could also describe with z being a function of x and y, we could have also used the local linear approximation. That probably would have been faster, but I wanted to practice this new way instead, and I want to confirm that it gave us the right answer. So we were looking at the point 1, 2. So if I were to find the local linear approximation, I would say, okay, this is going to be my function evaluated at 1, 2. So I'm just calling that function f of xy. Okay. Plus the partial of f with respect to x at 1, 2. Well, actually, let's write it this way. Plus the gradient of f at 1, 2, dotted with x minus 1, y minus 2. Let's work out the gradient. The gradient of f would just be f sub x, f sub y. Looks like that's going to be 2x, 2y. So the gradient of f at the point 1, 2 is going to be 2 times 1, 2 times 2. So this becomes L of xy is equal to f of 1, 2. That's my 1 squared plus 2 squared. That's 5. Plus my gradient is 2, 4, dotted with x minus 1, y minus 2. So remembering that L of xy is just a fancy name for the z value on the tangent plane, this becomes z equals 5 plus 2 times x minus 1 plus 4 times y minus 2. What I got over here looks like what I would get if I subtracted everything that's on the right-hand side on over. I've got a positive z. If I subtract over 5, I'll get a negative 5. If I subtract this term, I'll get a negative 2 times x minus 1. And if I subtract that, I'll get a negative 4 times y minus 2. So kind of neat just to see that, yep, it does work. We could find it either way. And there will be some surfaces where we really do need to use the parametrization. This is one where it probably was actually a little bit faster just to do the local linear approximation.